Okay, let's get started for today. Let's start with a recap of what we covered last time because we're going to be building very heavily on Wednesday's concepts. So we talked about online reinforcement learning, where we collect a batch of data with some policy by running that policy in the environment. And then we try to use that data to improve our policy. And then we repeat this process in order to get continue to improve from practice. We talked about an online reinforcement learning algorithm called policy gradients. And the update for our policy looks something like this, where we first take samples from our policy. This will give us n different trajectories sampled from our policy. We will evaluate the log likelihood of the policy. And so this pi here is representing a distribution over actions given states. And so this is looking like the gradient of the log probability of the actions under the policy. And this log likelihood is weighted by the reward that the agent got. And so if you have higher rewards as an outcome of your actions in the future, then you're going to be encouraging the policy to increase the likelihood of those actions. And then lastly, we introduced a baseline, which we could define to be the average reward, such that we're increasing the likelihood on futures that were above average reward and decreasing the likelihood on futures that, on actions that led to futures that were below average reward. So you can think of this sort of as encouraging the policy to do more of the above average stuff, less of the below average stuff, and then repeating that process to get better and better. Cool. We also talked about how this algorithm is fully on policy. So we need to, in order to evaluate this, we actually need to have samples from pi theta from our current policy. And this meant that we could only take one gradient step per batch of data, which is disappointing because then we'd have to collect a ton of data in order to improve. This kind of brings up this notion of having on policy versus off policy algorithms that can reuse data from other past policies. And we started to look at ways to make an algorithm off policy. And in particular, we talked about using importance weights, where if we weight the objective by the probability of the actions of the new policy divided by the probability of the actions under the old policy, this is a way to get an estimate of the gradient for the new policy. I should also mention that importance weights, the math behind it is very simple and very nice, but it's important to remember that this isn't a silver bullet. This sort of approach is only suitable when the policies are very similar to one another. And if the policies are very different, then this ratio will get very large or very small, and you'll also just have a worse estimate of your gradient. Okay, so today we're going to be talking about a form of algorithms called Actor-Critic methods that build on policy gradients. And we'll talk about, as part of this, we'll be talking about how to estimate the value of a policy. And then we'll introduce an off-policy variant of the algorithm. And these Actor-Critic methods are the basis for algorithms like PPO, which are used to train language models and that are used to train like humanoids in simulation, and so forth. So very, very useful RL algorithms. And then the key learning goals for today is how to estimate how good a state in action is for a policy. This is called policy evaluation. It's a critical aspect of Actor-Critic methods, but also useful more broadly. And then also talk about how to use those estimates to form a better reinforcement learning algorithm. Cool. So let's get started. And to talk about these algorithms, we need to revisit some very useful objects that we talked about in the first lecture. And specifically, this is value functions. And so a value function is representing how good a state is if you're going to follow a policy starting from that state. And you can think of it as the sum of rewards starting from, you start writing gradients, starting from some state. So we'll write this as v pi of s. This means that we're going to be starting at state s and then running pi. And for a given state, this is equal to the sum of rewards if we were to start at state t and go to the end of the trajectory. And here's the sum of rewards. Now, this sum of rewards is going to differ depending on what state we start at and depending on what policy that we're running. And so this is going to be an expectation of under our policy. Actually, maybe it's easier to write this as expectation on the inside. So this is an expectation over the states st prime and actions at prime that will be visited under our policy and conditioned on the fact that we're starting at state st. So we can think about the value function as this. Just in terms of math, what you can think about this as is, or just in terms of like conceptually or in terms of intuition, if you have some trajectory and you're thinking about the value of this state, you can think of it as if we were to collect a lot of different trajectories starting from that state from our policy, and then we just summed up the rewards from this time step to the end and then averaged over these trajectories, that would define the value of the state or how good the state is for the policy. Another useful quantity that we'll be making use of is called the Q function. And this is slightly different from the value function, but very closely related. And the difference is that instead of just thinking about the value of a given state, we're going to be thinking about a value of a given state and action. And what this is referring to is if you were to, instead of starting at S and then running pi from there, if instead we were to start at S, take a particular action A, and then run the policy, what is our expected sum of rewards? And so then you can think of this as instead of if a picture like this, say we had some state S that we considered, and first we're going to take some given action. This may or may not have been what the policy would have been likely to choose. This action could actually also lead to different states if because the environment is stochastic, and then it's the sum of these rewards on average. So this is what V looks like. This is what Q looks like for a given action. So here are some pictures on the slide. So if we start from state S, run our policy, we compute the expected sum of the rewards along these trajectories, then that gets us the value of a state. And then if instead we take action A first and then run pi, then we get the Q values, and it's just the sum of the rewards if we had started with action A. Now, one thing that's useful to think about in terms of how these two relate to each other is you can think of the value of a state as if you take an expectation over the actions that the policy would have taken, you can think of it as the average or the expectation of the Q values over all the actions that the policy would have taken. And then one last object that we'll use today is thinking about how good is a particular action relative to other actions that we might take. And for this, we can think about like if you consider the Q value minus the value function, that's going to tell you like how good is it to take action A versus following the policy at a given state. And this is kind of like what is the advantage of taking one action versus following the policy. Good question. So the question was, is there a normalization between V and Q? You can think of an expectation as an average. And so in that sense, there is going to be a normalization. Because if you were to, like, for example, try to estimate this expectation with samples, you would take some number of samples. If you only use these 2 samples to estimate Q, then you would divide by 2, versus here, if you're using 5 samples, you would divide by 5. Is there a way that you can get from this equation to the useful relation on the slide? Is that what you're asking? Yeah, so if you write out we can write out first what Q pi looks like. So Q pi of a given state and action, we're going to assume that we're going to condition on ST AT, because that's where we're starting. And then this is the expected sum of rewards if we, so a sum over T prime equals T to T. And then we're going to have an expectation of running the policy here, and then a sum of rewards. And then in terms of seeing how to get between these 2 things, this is you can think of this as a sum of rewards of under AT sampled from, or kind of future actions sampled from pi, whereas this one, AT, is not sampled but from pi, but all future actions are sampled from pi. In this case, we're kind of conditioning on the action that's kind of provided as input. In this case, we're sampling from the policy. And so if instead you sample the action from the policy and then feed that in to here, then you'll get this right here. Okay, so to help you start thinking about some of these quantities, let's look at an example. And so say that you are this person right here. You really want to learn how to play the drums. And your reward is 1 if you can play the music in a month, and 0 otherwise. So capital T is a month from now. And your action space, you have 3 different possible actions in your action space. One action is to sit on the beach. Another action is to watch TV. And another action is to practice playing the drums. And say that your current policy right now is just to sit on the beach. And you do that for all states. Now, my question for you to think about is, what are each of these quantities for the action of A1, for the action of A2, and for the action of A3? And so specifically, you want to think about what is the value function of your current state for this policy? What is your Q function for if you were to follow each of these actions and once and then follow this policy? And then what is your advantage function for the current state that you're in and for each of these actions? And you can assume that in the current state that you're in, you do not know how to play the drums. What was described is for the value function. For this particular policy that's always sitting on the beach, the value is 0 because the person would not learn to play the drums. So that's the sum of expected rewards for this policy for V pi. For the Q function, if you sit on the beach at the current time step or watch TV, the Q function will be 0 for those actions. Whereas if the Q function for playing the drums at the current time step would be 1 if that amount of practicing is sufficient. It's also possible that it would be a bit lower than 1 if you, for example, practice for like an hour and then sit on the beach by following the policy afterwards. It kind of depends a little bit on what the time, how long a given time step is. And then the advantage function is going to be Q minus V. And so it's going to be a positive number for the action of practicing, and it'll be 0 for the other 2 actions. Yeah, so the question is, if practicing is not enough to actually learn, would it be 1? Would it be between 0 and 1? Would it be 0? It basically actually represents the probability in which you would be able to play this, given that you had practiced for that amount of time. And that probability It could be 0, like maybe this is like really, really hard after just practicing once. It could also be like maybe for someone who's like extremely talented, they only need to practice once. And so that could be a bit higher for someone that's like a bit more talented. It depends on various factors like that. Yeah. Kind of along those lines, if you think about the value function, for like, if you're playing like a game of chess, for example, the value function is the probability that, you're going to win for a given person and for a given game state. So it's kind of evaluating, how good is the state for a particular person. That's another way to think about it. Okay, cool. So, those are the objects that we're going to be using quite a bit today. Now let's go back to policy gradients and see how we can use value functions to make this algorithm better. So we talked about a couple examples on Wednesday of some scenarios that were dissatisfying about policy gradients. And the first was that if we are trying to learn how to walk and we have a policy that takes a small step forwards and then falls backwards, we will push down the likelihood of taking a step forwards, because we don't necessarily know that might have led it to fall backwards. Now, if we actually had some understanding that taking a small step forward was making progress, was actually good, was advantageous, then we might be able to actually increase the likelihood of that. And so this is starting to hint at some of the intuition behind actor-critic methods. And likewise, we talked about this example of trying to fold a jacket, and we found that if you have a sparse reward and you only do part of the task, like folding only the sleeves or flattening the jacket but not folding it, you aren't really utilizing the trajectories that are getting 0 reward. And kind of similar to this case, if we instead kind of understood that these actions are advantageous for making progress on the task, then we might actually be able to figure out how to use these trajectories in a positive way. And so kind of to summarize here, policy gradients don't always make an efficient use of data that we've collected. And if we can try to figure out what actions are advantageous versus not advantageous, we might be able to make better use of that data. So the question was, if it's not clear if a step forward is helpful or not, is that going to be negative or neutral? In the case of the policy gradient, in case of this policy gradient algorithm, the trajectory that we considered here in the context of the batch of trajectories was kind of net negative, was below average, because the reward to go is quite negative. It's actually making backwards progress in this trajectory. And so it actually is going to be pushing down the likelihood of taking a step forward because the future reward to go is negative. And what we'll talk about today is algorithms that in principle could actually increase the likelihood for taking the step forward and decrease the likelihood for falling backwards. Okay. So how do we do that? A lot of what we'll focus on today is this piece right here. This is what's actually telling us that we should push down the likelihood if we have negative rewards in the future. And this quantity, it's estimating the future rewards if we take action A in state S. And so we can kind of think about it as in this picture right here. It looks a lot like what is the sum of rewards if we started right here with state S and action A. And then if we think about this picture, we were looking at this quantity in terms of like what we observed in trajectories, but what would be an even better version of this quantity would be to actually use the Q function. And if we could replace this with the Q function, then we would be able to get a much better estimate of whether or not we should push up the likelihood or push down the likelihood. And so looking at the slides right now, what we do is for like a single trajectory, we sum together the rewards that we saw, which was in the case, the example before, the rewards were negative because we took a small step forwards and then fell backwards. But if instead what we could do is actually run the policy many, many times and get a Q function for the state, that would be the true expected rewards to go under the expectation of our policy. And this would be way better. We'd be able to get a much better sense for how good it was to take that action in that state. So essentially the form of the gradient would be able to get a much better gradient if the form of the gradient looked like this, where we increase the likelihood of the actions for things that have high Q values, and we decrease the likelihood of the actions for things that have low Q values. So that's kind of a first step. Now, taking things one step further, we also talked about baselines in the previous lecture, where the baseline was the average reward. Should we use a baseline here? So before the baselines were the average reward. And so in this case, if we were to introduce baselines, we could think about what we might use. And if we use the same thing that we used before, we could use like the average Q value in this case. So we could use an average, like maybe we sample some SI and AI, and we average over those. And what we had talked about a few slides ago is actually, this is actually looking a lot like the value function. So we talked about the value of a given state is an expectation over actions sampled from the policy for that given state of the Q function for those actions. This is V pi. And so a natural baseline would actually be to use the value function. And so we could have, instead of having this be Q values, we could actually use Q minus V. And Q minus V is what the advantage function is. And so putting this together, we would be increasing the likelihood for actions that have a high advantage and decreasing the likelihood for actions that have a low advantage. And so then if you think back to the example of learning to practice playing the drums, we would be increasing the action of practicing had a high advantage relative to the current policy. And so then we would choose to increase the likelihood for practicing and decrease the likelihood for the other actions. Cool. And another way to think about this is that better estimates of this advantage function will lead to less noisy gradient. And if we knew the true advantage function, then we would be able to get a very, very good gradient. Unfortunately, we don't know the true advantage function. And so the next question that we'll talk about over the next several slides is how can we estimate the advantage function? Right. So the question was like how is this different from like how we're sampling in the original policy gradient? And so what we were using before is we were doing this, like we would take kind of one sample and then for like a given state and action in that trajectory, we would sum the rewards just for that individual thing. And now what we're saying is that instead of, and this is going to be like a very noisy estimate because we just have one trajectory here. We just have one data point to estimate these rewards. And now what we're saying here is that we're going to try to get a sense for what the advantage of this action is. Now, one way, we'll actually start to talk about how we do that in a minute. But if you want to think about what is the true advantage of this action, conceptually, if you were to take this state in action and then roll out the policy an infinite number of times for this action versus for following the policy in other scenarios, that's what would give us the advantage. Yeah, so the question is, in policy gradient, we got to where we were by optimizing the expected sum of rewards. Does this also optimize some objective? So this is also optimizing the expected sum of rewards. It's actually optimizing the same exact function. We haven't talked about how to get A yet, but if you had a perfect A, this would also, like, this would be giving you the correct gradient for that objective. Modulo kind of the sampling here being used to sample states and actions. Is the baseline an average over the current trajectory or an average over all trajectories? Yeah. So if we set it to be the Q function, the value function V, that would be like an infinite number of samples. We haven't yet talked about how we're actually going to estimate A, or estimate Q versus V. So we'll talk about that in a minute. But yeah, for V, like conceptually that would be like over an infinite number. But I'm talking about like this is the true value so far. We haven't talked about how to estimate the value yet. Yeah, so the question is this unbiased? It is unbiased. You can go through the math. I won't go through that today for the sake of time. But yeah, this is an unbiased estimate of the gradient if you have the true advantage. Now, we will see things that are biased later today. Okay, so let's actually talk about how do we use this. And actually, just as a quick overview of what the algorithm will look like for this form of algorithm. Before we had this loop between running the policy and improving the policy. Now we're going to have an additional step where we're going to fit a model that's going to estimate the expected return. And essentially it's going to try to estimate this A right here. And so our new algorithm will have a few different steps. One is to run the policy. One is to try to estimate values. And then the last will be then to use that estimate and the data that was collected to improve the policy. And so this step will involve estimating either VPy, QPy, or APy. And this step will be kind of similar to before, except it's going to use these estimates right here. Okay, so let's get to how do we actually estimate these values. So we want to estimate this quantity right here. And to start out, we need to think about how we want to get to APy. And we could try to directly fit APy, although it's actually a little bit challenging to get direct supervision for the advantages. And so we're actually going to try to fit VPy. And the way that we're going to get there is let's see, where do we want to go? We know that APy of STAT is equal to the Q value minus the value. And so one option is we could try to estimate these two, although then we'd still have to estimate two objects. And there's actually a way to turn this into an equation that actually only depends on VPy. And that would be nice because then we could just only fit VPy and then derive APy from there to get the gradient. And so to do this, we can think about QPy right here. And this Q function, this is the value of starting in S, taking A, and then summing the rewards. And so you can think of it as the reward at the current time step that you got, plus the rewards that would come after that. And in terms of the rewards that would come after that, you'll have some next state, ST plus 1. And so you can think of it as there's some next state. You don't, there's actually some, this next state could be a few different things depending on your environment. So this would be sampled from the dynamics of the environment. And then after this state, it's essentially going to be the sum of rewards starting at ST plus 1 and following your policy. And the sum of rewards starting at, this should be ST plus 1. The sum of rewards starting at ST plus 1, that's equal to the value, right? The value of ST plus 1. So we can write the this Q value as the reward at the current time step plus the value at the time step after that. Now, we can't sample from these dynamics, but when we ran our policy to collect data, we did actually see one outcome, one ST plus one. And so we can approximate this as the reward at the current time step plus the value at the next time step. And then if we want to estimate the advantage, we can write it as the reward at the current time step plus the value at the next time step minus the value at the current time step. And so maybe I'll do this in a different color to differentiate it. So now a pi can be written as of STAT can be approximated as the reward that you saw plus the value at the next time step minus the value at the current time step. And so if we then have an estimate of V for our policy, then we can estimate the advantage and we can just try to directly fit V. And so on the slides, what this looks like, we have Q. Q can be written as the expected future rewards, which is the reward at the current time step plus the future rewards. These future rewards can be written as the value. And so we can think of Q as the reward at the current time step plus the value at the next time step. So why is the second to last line, why is this an approximation? The reason for this is that the next state, there's actually multiple possible next states, and we're just going to use one sample from this expectation, which is the sample that we saw when we rolled out the trajectory in our data. And if you wanted an exact thing, you would need to estimate this expectation with like infinite samples. How good of an approximation is this? So it is going to be a single sample approximation. The good news is that later on we'll see ways to use lots of data to do this. And so it's in general, so I guess the first thing is that if this is very deterministic, it's going to be a good estimate because there aren't that many futures. If it's more stochastic, then it's going to be a worse estimate. And then we'll see ways in which we can use data and take lots of gradient steps in a way that makes it not too bad. So the question is there any new interaction with the environment? So I guess we haven't yet talked about how to fit VPy. So we will talk about that in the next slide. Yeah, so if you have some trajectory, this will be like the ST, AT, and ST plus one in your trajectory from the same trajectory. Yeah, so you need to use the same trajectory for this. And sometimes I forget to put the pi on here. And there is a lot of reinforcement learning work that drops the pi's just for simplicity, but it is actually in some ways very important to have a pi there because it is estimating a value for a particular policy, not for any policy. So the question is, why are we choosing to estimate V versus Q versus A? It's just a little bit simpler in practice, but you can also, there are also ways to directly estimate Q, and actually we'll talk about some of those ways next week as well. Okay. Cool. So we're just going to fit VPy, and then once we fit VPy, we can get the advantage and then plug that into our gradient for our policy. We can represent VPy as a neural network, and what this will look like is we'll pass as input a state, and then it will output a single scalar value, not as pictured here, that's a single scalar value that represents the value of that state for that policy. This neural network will have some parameters. So how do we do this? So there's a few different ways to estimate VPy. The first version, so in the very, very initial version, like of vanilla policy gradients, we just used a single trajectory, a single sample. And we kind of, instead of actually learning a model, we just used that sample. In principle, we could also use many samples and then use many samples. Unfortunately, if you were to try to go to a particular state and then take many samples from that state, that means that you would have to be able to kind of reset the world to that state and kind of see what happens if you took many different rollouts from that same state. And unfortunately, in many scenarios, it's very hard to reset the state. If you are in kind of simulated settings, sometimes you can actually reset the simulator. So there is sometimes scenarios where you can do this, but in practice, we typically don't do this. So since we can't like kind of directly reset and take lots of samples, what we can do is we can use multiple trajectories that we had sampled and just train a single model on the original single sample estimate. And because our kind of the trajectories that we have, they will have some states in them that are similar. You'll be able to essentially learn how to kind of like amortize the data. So you'll see some examples in the environment that have very similar states and have kind of corresponding future rewards in them. And with that repetition in your data, a neural network can actually learn, kind of have a little bit more density in terms of the rewards that you'll see for a given state. And so what this is going to look like is you can take your data set and for all of the, you'll have like I equals 1 to n trajectories, and each trajectory will have time steps in it. And for all of those trajectories and time steps, you'll also have some sum of rewards that you observe for that. So you'll have some sum of rewards that started at t to the end of the rewards of the states and actions that you visited. And if you aggregate kind of all the trajectories in your data set, you can train a model to go from the state that you saw to the sum of rewards that was observed when you ran the policy. And with this, you can kind of form a supervised learning data set where this is the label in the data set. And you can train with supervised learning a model to take as input this and output this quantity right here. And the number of data points in your data set will be the number of trajectories times the average number of time steps. Yeah, so the question is, each time your policy changes, do you have to kind of recollect the data and refit this? With this approach, yes. We will see approaches later. This is like the simplest and kind of dumbest approach you can use to fit a value function. And we will see approaches where you can kind of reuse other data. Yeah, so the question was, if we're going to be running a lot of kind of simulations or rollouts of our policy, is it like unreasonable to try to learn some estimate of like future states given the current state in action? The two things here, if you have a very simple state space, a very small state space, you might be able to kind of store some things and kind of form an estimate just from storing things. You could also, in principle, train a neural network to predict what future states would be given current states and actions. There are a set of approaches that use those, that do that, and they're called model-based approaches, and that they're learning a model of the world. And we will talk about those approaches in a few weeks. Okay, so this first approach is just to aggregate, kind of run a bunch of samples, aggregate a data set of our future rewards, and then run supervised learning to fit an estimated value function where you can form a kind of an L2 error between your predicted value and the observed sum of rewards, and then minimize that with respect to the parameters of your value function. And so what this objective looks like is minimizing with respect to your parameters, the difference between your predicted value and the the example or the sum of rewards that you saw in your data set for a given I. And you'll do this for all of the data points in your data set. And so this actually can also be a sum over I and t, just for completeness. So that will be kind of the objective, and you can run gradient descent on this objective to fit a value function on your data point. Do we need to train a neural network for every gradient step in this case? So this is actually different from policy gradient, where we, when we change, the gradient steps here that we take are going to be trying to fit a value function, and the value function isn't changing the policy. And so you can actually take many gradient steps on this objective to learn a value function without having to recollect your data. Cool. So this is the simplest approach for training a value function. It's called Monte Carlo estimation, where essentially you're just running lots of simulations, running lots of rollouts, and then trying to learn how to predict the outcome of the future rewards. Now, there's actually an approach that's better than this. And in particular, when we think about these sum of rewards, maybe it's helpful to draw a picture in this case. So we have like a bunch of trajectories that we have sampled. And in this case, what we're doing is when we have a kind of a state right here, we are summing the rewards here as the value. And as we're learning this, we're kind of starting to learn what the value is, what the value of a given state is. And this means that the maybe halfway through training, when we're regressing to future rewards, and if we start to get kind of what is a good value of like this state right here, then we can actually try to use our own estimate of this value as the supervision target. And in particular, if we know that the reward, we got a reward at this time step right here to then get to here, then we could actually use that reward plus our estimate as the supervision target rather than just using the sum of future rewards. And so, in particular, the ideal target is the sum of, like the true sum of expected rewards. This is equal to the reward at the current time step plus the expected rewards at the next time step. And this is equal to the sum of rewards at the next time step is equal to the value of the next state. And so, in principle, what we could do is instead of trying to regress to future rewards, we could regress to the reward at the current time step plus the value at the next time step. And so we're actually going to be, in this case, using our estimate of the value at the next time step as part of the supervision target. So this would be, these are all for a given trajectory, and this would be your new label for your data set for a given state. Yeah, so the question is, how often do you update these VPIs? In practice, you can update them like every single iteration. If it's like really expensive to update them, you could update them less frequently, like if you have a really huge neural network. But in practice, typically we update them every single gradient step. So we have these kind of bootstrapped estimates. We refer to this as bootstrapping because we're actually kind of bootstrapping off of our own estimate of the value function as part of the learning process. We formulate our training data. We're then going to use the same exact objective to fit a value function, just regressing to these targets. We just have different labels in our data set now. And these labels are changing as we are changing as we kind of run gradient descent on our objective. And so you often will update your labels every single gradient update. So the question is this based on like one trajectory, or is this based on kind of multiple trajectories where things are close together? So this data set will be over multiple trajectories, where I is indexing over trajectories and T is indexing over time inside those trajectories. In terms of this label, this will be for a given data point, and it will be you're not going to be running multiple simulations from that data point, but you're going to be kind of estimating what would have happened from your future state rather than a single sample of what happened in that trajectory. And so with this, you're actually able to get a better estimate of all of the possible outcomes that might have happened at the next state rather than just one outcome. So you're asking, why is the input to the value function just S and not including previous time steps? So in this expectation, this is representing, so for, the ideal target for our value function is the sum of future rewards. And you can think about this sum of future rewards as, the reward at the current time step, which is a deterministic quantity, plus the future rewards, for our, conditioned on our current state. And so this is conditioned on the current state because the future rewards is a function of where we are right now. And it's actually only a function of where we are right now and not anything else. Yeah, so the question is, does this require that you have like a good initial value estimate? Because if it's really bad at the beginning, then your targets will be really bad. There are some considerations when initializing it, although oftentimes you don't need to do anything like super fancy to initialize it, and you can just get started training on this directly. You probably don't want to initialize your neural network such that like the values are like -1,000 or something. Like that would be bad. But usually we don't initialize our neural networks that way anyway. If I don't know if I've like in practice seen any issues with this, but in principle, you could also start with a Monte Carlo objective just to get it in the right ballpark, and then continue with this update after that. So is this part of backpropagation, and is there a better way than updating the labels every step? So we'll be using backpropagation to optimize that objective right there. You could also think about this as like propagating information backwards in time, which is distinct from like propagating gradients through the network. The one other name for this is called temporal difference learning, where we're like looking at the difference between the kind of future time step and the current time step. But it is like generally is like kind of propagating information through time is like fairly distinct from backpropagation. To summarize what we've talked about so far, Monte Carlo, we're supervising with the rollout summed rewards, whereas bootstrapping, we're supervising using the reward plus the current value estimate of the next state. And if we look at an example, and actually, yeah, I'll give another kind of exercise for you to figure out. So let's look at an example. So we've run the policy. Maybe we just have two trajectories. In practice, we'll have more than this, but say we have two trajectories. One of these trajectories, the final reward was -1. The other trajectory, the final reward was 1. And along the trajectory, before the final state, the reward is 0. My question for you is, what estimate would we get for two different states for the value function? And in particular, if we were training on just these two trajectories, and we use Monte Carlo versus using temporal difference or bootstrap learning, what would we estimate the value to be for the blue state for these two? And what would we estimate the value to be for the pink state for these two? Yeah, so for Monte Carlo in the blue state, it's going to average out the -1 and the +1. And so this prediction will be 0. Does anyone want to share another one? Yeah, so for the Monte Carlo for this one, this will be -1, because it will be kind of supervised to predict the sum of rewards for the future for this trajectory. Anyone want to share? Wait, maybe before we do that, let's talk about, do you want to do this one? This is a little bit more intuitive to go this way. Okay, yeah, so this will also be 0. And then does anyone want to do the back right? Yeah, so for this one, it'll see this kind of blue one in the future. This will have a 0, and then this will also be assigned the hat of 0. And so this is an example of where Monte Carlo and the bootstrapped estimate are going to be different. And arguably, we get a more accurate estimate from the kind of bootstrap value because it's able to kind of look at its estimate of the value and actually aggregate information across trajectories more effectively. Why the Monte Carlo is -1 by the top right. Yeah. So the value for this one is going to be -1 because the Monte Carlo objective is supervising to the sum of future rewards that are observed for each trajectory. And so for this trajectory, which is black, it only sees the sum of future rewards along this trajectory. So it only sees -1. And anything over here along this trajectory for Monte Carlo would have a target of 1 because it only sees the future trajectories here, and it doesn't use because it doesn't bootstrap off of its estimate that was using all of the trajectories. Yeah, so the Monte Carlo blue state, it's going to be that exact state is in the buffer or is in your data set for both trajectories, and so it's going to average the reward for them. But this is like the only scenario where Monte Carlo is going to kind of get information from both trajectories because you have the same exact state in your data sets with 2 different labels. Why is the bootstrapped blue state 0? So this is also going to be averaging the future rewards. It doesn't have anything necessarily special to bootstrap off of. And so kind of for the same reason that Monte Carlo is 0, this will also be 0. So basically everything after the blue state will have a value estimate of -1 here, and everything after the blue state on the black trajectory is going to have an estimate of -1. Okay, we should move on. So kind of one question you might ask kind of looking at this is there might also be a middle ground. So Monte Carlo is going to have high variance, but it is completely unbiased. Whereas the bootstrapped estimate has much lower variance, but it actually can be incorrect because your current estimate of the value function is going to have inevitably at least a small amount of error in it. And so maybe there's a way, there might be a way to potentially balance this bias and variance a bit more. And one way that we can think about this is if we have our trajectories, we can think of the Monte Carlo version as using the sum of rewards averaged over those trajectories. Whereas the TD version is going to be looking at the first reward plus the value right after that. So it's kind of R plus V for just a temporal difference of just 1 time step. And you can actually sort of interpolate between these 2 estimates. And instead of using just 1 time step, you could use n time steps. So you could look at the reward for n time steps, sum the rewards for n time steps in the future before the variance has increased substantially, and then use your value estimate after those n time steps. And what this would look like is an equation like this, where instead of just using 1 reward right here, and instead of using all of the sum of rewards, you can sum over the next n-1 rewards, and then use your value estimate at t plus n. And so this looks like a sum over from t to t plus n minus 1 of r of s a plus your estimate of the value at t plus n. And this would be, in this case, is going to have a lot less variance than the full Monte Carlo, especially if you have smaller n. And it's going to be potentially a little bit less biased than just using a 1-step temporal difference bootstrap. And so you're essentially going to have more information about the rewards that were directly observed. So this can be written as this. And in this case, this now becomes your target for supervised learning. And yeah, this is often called n-step returns because you're summing over n time steps. In practice, often using, if you set n equals 1, this is just the bootstrap version. If you set n equals t, this is full Monte Carlo. Oftentimes, somewhere in between 1 and t works the best in practice. And this can be especially useful in scenarios where you have very small time steps. Because if your time step is like, I don't know, 10 milliseconds or something like that, then very little will have happened in between those time steps. If you have a very long time trajectory, can you use like both of these, you're asking? Oh, yeah. You could also like add to your data set, like you could add all of these to your data set in principle. I think that typically like the high variance like labels, like the things that are like high variance can deteriorate learning because it leads to more stochasticity, and likewise like having like if your values are like not very good, then this can also be a challenge. And so in practice, you'll usually just pick one of these versions and supervise with that. In principle, you could combine them, but yeah, in practice, usually you don't. Okay. One aside here. So, so far we've been summing rewards, and we actually talked in the first lecture about how in some cases we might not want to just blindly sum all rewards in the future. And in particular, if you think about scenarios where the length of the episode is like infinite, or very, very long, then your estimate of the value can get very large in those cases. And so you might not want to just be summing over all of the rewards in the future. And so a simple trick to handle the fact that your estimates of the value can get very big is to weight your objective, weight the sum of rewards to be biased towards the earlier rewards. And the way that you can write this is instead of having r plus v, you can add a coefficient right here, where if this coefficient is 1, it's the same as before. But you can set it to something like 0.9 or 0.99. And what this is going to do is it's going to say that I care more about the rewards at the current time step and less about the rewards at the future time steps. Adding this discount factor that's discounting future rewards, this actually can be viewed as changing the decision process slightly. So it's actually equivalent to saying that there is kind of some probability that you will, that the agent will kind of die at any given point in time. And so this is equivalent to saying that, with some probability, so say gamma is like, 0.99. In this case, using this form is equivalent to saying that there's a 1% chance that the agent will enter some state that has 0 reward and stay there forever. And so if you have like some original MDP right here, the way that this discount factor would change the MDP is it would say that with some probability, with a probability 1 minus gamma, you enter this kind of death state that doesn't, where you can't do anything else after that. And the probability of, the original probabilities in the rest of the MDP are all multiplied by gamma. The question is there any relationship between gamma and like these n-step things? Like if that gamma is small, would that change like what you do? The way that you would modify this objective would be gamma to the n. Possibly, I mean, I think that they're all interconnected in the sense that the choice of gamma might depend on the environment. And generally, if you're going to be looking further into the future, maybe that's because you're going to be in an environment that's more deterministic or has smaller time steps. And that would also affect the choice of gamma. So the question was, in terms of choosing how far you look ahead, does that affect whether you're prioritizing short versus long term? In this case, it is more a factor of So it doesn't actually affect like how greedy you are, because the value function is representing the sum of rewards. And so these are still estimating the same exact quantity. It's more a factor of like how far in the future are you looking ahead in terms of the rewards? And it's more a factor of like how much is the variance increasing? And if the variance increases kind of somewhat slowly, then you can look further ahead in the future. If it increases very, very quickly, then you might want to use a smaller n. Cool. So let's walk through the full algorithm now. So we talked about estimating value functions. Now let's actually like put this into practice. So what we can do is we can sample a batch of data from our policy. Then we will fit our value estimate to the summed rewards in the data. And we can do this by looking at the rewards for a short period of time and then the value. So this would be the equation for n-step returns. And then when we fit this, we'll run multiple gradient steps on this objective that's trying to minimize the difference between our estimates and the observed future rewards. Then once we have our estimate of the value, then we can use that to estimate the advantage of a particular action by looking at the reward plus the value at the next time step minus the value at the current time step. This is telling us how, according to our value function and the reward we saw, how good is the action that was taken in the data set. And then we can use this to get a gradient for our policy, where we will be increasing the likelihood of actions that are estimated to be advantageous and decreasing the likelihood for actions that are not advantageous. And then lastly, we'll update our policy by applying this gradient step to our policy parameters. And then we can repeat this process to then sample a new batch of data for our policy. Now, note here we have two neural networks. One is for the policy and one is for the value function. This is called an actor-critic algorithm because one of the networks is the actor, one of the networks is the value function, which can also be called a critic because it's criticizing how good a state and policy is. And that's our algorithm. And coming back to the examples that we saw before, this is something that's able to actually make use of data, for example, that takes a step forward and then falls backwards, because you can actually learn from the data, especially when you use bootstrapped estimates, that taking a step forward is advantageous and has a positive advantage compared to other actions that you might take. And so this is going to be making much more efficient use of the data that we've collected. Cool. So review so far, we've talked about policy gradients, which is trying to do more of the good stuff, less of the bad stuff based on what you observe. Actor-Critic are learning to estimate what's good and bad and then doing more of the good stuff according to your estimate. And we can get a better estimate by using a neural network to try to explicitly estimate the value function. And then we introduced kind of this third step where we are fitting this model as part of the improvement process. We talked about 3 different ways to estimate value, either directly looking at summed rewards, bootstrapping off the value function, and this hybrid. And this is often referred to as policy evaluation.